Scana Steel Bjornborg operates a fully integrated production line specializing in large forged steel components. The process begins with melting scrap steel and alloying elements in an electric arc furnace, EAF. This method provides excellent control over temperature and metallurgy, essential for producing high-purity steel. Once molten, the steel is refined in a ladle furnace, where adjustments are made to ensure the proper chemical composition and removal of non-metallic inclusions, like sulfur, phosphorus, and oxides. After refining, the clean molten steel is cast into large ingots, which are carefully cooled and then reheated in high-capacity furnaces to the required forging temperature. The heated ingots are transferred to a high-tonnage open-die hydraulic forging press, equipped with overhead cranes and automated manipulators for precise control during forming. With press forces reaching several thousand tons, Scana can forge extremely large components such as turbine shafts, crankshafts, rudder stocks, and industrial rollers. The open die forging process ensures directional grain flow, reducing internal voids, and increasing mechanical integrity. Unlike closed die forging, open die methods are ideal for custom shapes and low to medium volume production. Scana's press line allows flexibility in shaping and supports a wide range of part geometries, with consistent deformation that enhances fatigue life and fracture toughness. Once forging is complete, components are transferred to computer-controlled heat treatment facilities. Depending on application-specific requirements, the pieces are subjected to normalizing, quenching, and tempering, or annealing processes. These operations refine the grain structure and improve mechanical properties such as toughness, yield strength, and elongation. Uniform heating and cooling are critical to avoid distortion or residual stress, especially in large cross-section parts. After thermal treatment, all products undergo a thorough, non-destructive testing regime. Techniques include ultrasonic testing for internal flaws, magnetic particle inspection for surface cracks, and dye-penetrant testing for detailed surface anomaly detection. Visual and dimensional inspections are also performed to confirm compliance. Scana ensures full adherence to international standards. In the final machining stage, components are machined using large-format CNC equipment capable of maintaining tight tolerances. Turning, boring, deep-hole drilling, and facing operations are conducted in-house, enabling complete dimensional control. Optional services include stress relief, custom surface finishing, and full mechanical testing, including Charpy impact, tensile, and hardness testing. Scana's integrated manufacturing model allows traceability from raw material to finished part, ensuring full quality control and transparency. With capabilities exceeding 60-ton component weight and decades of metallurgical expertise, Scana Steel Bjornborg delivers forged steel solutions for the most demanding industrial sectors, including marine propulsion, offshore oil and gas, hydropower, and defense. Every stage of production is supported by advanced digital monitoring, strict process control, and a commitment to sustainable high-performance steel production. The self-programming robotic welding system offers a highly automated and adaptive solution for structural beam assembly. The process begins with operators placing accessories onto a conveyor tray with the option to preload additional trays to enhance workflow efficiency. Each accessory, identified by cadesis, scanned using a 3D vision system to validate geometry and orientation. Handling trolleys and robotic manipulators automatically adjust their positions to avoid collisions with pre-mounted accessories. Simultaneously, the structural beams are scanned to detect any warping or distortion, allowing the system to compensate dynamically. Validated accessories are then precisely positioned and tacked onto the beam based on the digital model. The welding operation is performed using a robotic arm equipped with a vision-guided system that ensures accurate weld placement. The beam is rotated automatically, enabling access to all sides without manual repositioning. Once the beam is fully welded, it is transported to the unloading zone for further handling. The entire process significantly reduces labor input, improves weld consistency, and enhances productivity in beam fabrication application. The fixer turn system features a high-performance round insert with 6 precise indexing positions, ideal for roughing medium to large workpieces. Its secure toolholder design ensures accurate insert positioning, maximizing cutting efficiency, tool life, and operational stability in heavy-duty turning applications. The DMC65H monoblock by DMG Mori is a highly advanced 5-axis horizontal machining center designed specifically for high-precision and high-efficiency applications in the aerospace industry. Its configuration offers the flexibility of vertical machining with the process reliability and chip control of horizontal machining, making it ideal for aerospace structural parts that require both complex geometries and tight tolerances. The machine features a robust monoblock structure with a thermosymmetrical design and 3-point support that ensures long-term accuracy, stability, and rigidity. This allows it to maintain precision within 5 microns, even during continuous heavy-duty machining operations. Its B-axis swivel rotary table, supported on both sides, can handle workpieces weighing up to 600 kilograms, offering optimal positioning accuracy and enhanced accessibility for multi-face machining. The horizontal setup facilitates excellent chip fall and heat dissipation, which is critical for machining aluminum and titanium components commonly used in the aerospace sector. The DMC65H monoblock also excels in deep hole drilling applications, with capabilities up to 550 millimeters in a single setup, thereby minimizing repositioning and ensuring process continuity. To further enhance productivity, the machine is designed for seamless integration with automation systems such as the PH-Cell or RPS-12 pallet handling system. This allows for parallel loading and unloading, reducing downtime and boosting throughput in demanding production environments. The machine's tool magazine can house a large number of tools, supporting complex and varied machining tasks without manual intervention. Overall, the DMC65H monoblock delivers a combination of performance, precision, and automation readiness that meets the aerospace industry's stringent requirements. It is particularly well suited for producing structural airframe parts, engine components, and other precision assemblies that demand both material removal efficiency and geometrical integrity across multiple axes. The production of razor blades involves a precise and highly controlled series of steps to ensure durability, sharpness, and safety. It begins with the thermal process, where high-quality stainless steel strips are heated to increase strength and flexibility. This heat treatment enhances the blade's ability to retain a sharp edge while resisting breakage under stress. Once the metal cools, each strip undergoes inspection to ensure there are no surface defects or inconsistencies. Following inspection, the steel strip is passed through a coating process. Here, a thin layer of material, such as platinum or chromium, is applied to reduce friction and improve resistance to corrosion. After coating, the strips undergo sintering, a process where the coating is fused to the metal surface at high temperature, creating a uniform, durable layer that enhances blade performance. Next is the sharpness test, where each blade edge is evaluated to ensure it meets precise standards for cutting ability. This is critical, as even microscopic imperfections can affect the blade's efficiency and safety. After testing, the blades are soaked in anti-rust oil to preserve their condition during storage and transport. After testing, the blades are soaked in anti-rust oil to preserve their condition during storage and transport. A final quality inspection is performed, involving both visual checks and automated systems to confirm each blade meets all specifications. Blades that pass this phase move to the packaging stage, where they are safely encased, often with protective covers, and boxed for retail sale. Every step in the razor blade manufacturing process is engineered for consistency, ensuring each blade delivers a smooth and reliable shave. The Shellmaster is a dedicated machine designed for the efficient and accurate assembly of cylindrical steel tanks used in industries such as oil, gas, and water storage. The process begins by aligning and positioning pre-rolled steel shell sections using hydraulic arms and guide rollers. The shells are then joined together using precisely controlled clamping mechanisms to ensure consistent seam alignment. Next, automated systems perform longitudinal and transverse seams along the seams, creating a continuous, high-strength tank wall. The Shellmaster maintains tight control over roundness, verticality, and weld quality, reducing the need for rework. Integrated lifting systems allow the tank structure to be lifted to add the next shell. This modular, upward assembly method ensures that tank construction is fast, safe, and repeatable. The design process uses pre-engineered modular components to ensure flexibility and high efficiency. Rotor shafts are precision machined on Georg Alterturn 3500 megacoulombs. Multi-casing turbines, with or without reheating, are assembled with control extraction and achieve outputs over 200 MWe for various power plant applications. The fabrication process begins with oxy-fuel cutting of 3-inch thick carbon steel plates. The plates are then rolled into curved segments and formed into a 90-inch inner diameter. 6 sections are assembled and joined using ASME certified long seam and dual girth seam welding. This creates a 660-inch long pressure vessel cylinder, ensuring structural integrity and compliance with standards. The production of rail steel shovels begins with cutting raw materials from high-carbon railway rails that meet GHOST R standards. These blanks are heated and hot forged into shovel shapes. A unique dual hardening process is then applied, involving precise heat treatment that reduces volatile carbon loss to mere fractions of a percent. As a result, the steel retains its carbon content, enhancing both strength and elasticity. The footstep section is ergonomically designed to match foot anatomy and transitions into the socket, tuleka, serving as an additional stiffening rib. The socket features a special unsealed seam that tightly grips the wooden handle, accommodating changes in wood humidity without losing stability. The spring-like properties of the steel prevent excessive stress at the joint under pressure. Each shovel is coated with a high-strength lacquer to protect against corrosion. The edges are sharpened to enable the shovel to self-sharpen during use, allowing it to cut through tough materials like ice, wood, or softer metals. A logo is stamped on each shovel for traceability. Every product undergoes strict quality control and is certified to meet international standards, with a wide variety of models offered for various tasks. Aluminum is hot rolled. Head and tail are cut off. Then it's cut to required size and cooled to complete the rolling process. The 7-meter, 600-ton EHT single-span hydraulic press brake at Macquarie Engineering Limited folds long metal sheets with high precision. Operators load the sheet onto the press bed, align it using CNC-controlled back gauges, and activate the machine to apply up to 600 tons of force. The press brake bends the sheet along programmed lines using interchangeable tooling. This process ensures tight tolerances and consistent angles across the full length of the component. The construction of the 15-story hotel in less than 6 days was carried out by a 200-worker team assembled prefabricated components to erect the 15-story structure in 46.5 hours, then completed external cladding and interior finishes in another 90 hours. Aluminum folding door manufacturing process. First, aluminum profiles are cut to size using a CNC machine. These profiles are then machined to form hinges, locks, drains, and hardware. Next, the profiles are assembled to form the door frame and outer frame. Corner joints are mechanically secured and reinforcing bars may be inserted for additional strength. During installation, precise measurements are taken on site to ensure a perfect fit. The prepared profiles are aligned and secured to the opening with the appropriate pins and fasteners. Hinges, rollers, and handles are carefully installed to allow smooth folding and sliding movements. The profiles are then hung on the frame, adjusted for leveling and clearance, and tested for proper operation. Gaskets and seals are installed to ensure airtightness and weatherproofing. The first sector module of tokamak was extracted from the sub-assembly tool, lifted and rotated 90 degrees to pass a wall into the assembly pit. The 1,380-ton load comprising a vacuum vessel sector, D-shaped coils, thermal shield, and piping was moved with minimal clearances, down to 4 centimeters in some areas. A 50-person team coordinated the operation using 3D models, sensors, and laser tracking. Vertical clearance over the pit wall was just 20 centimeters. The module was carefully lowered into the 30-meter deep pit, compensating for pendulum swing, and finally positioned with sub-millimetric precision onto its supports. The round pipe is fed into the steel square tube making machine, where it undergoes cold rolling. Through hydraulic pushing and squeezing, it passes through a series of active or passive roller frames equipped with horizontal and vertical rollers. These rollers reshape the pipe gradually into square profiles. For smaller sizes, active rollers are used, while larger pipes utilize a passive roll unit with hydraulic thrust. Finally, the shaped pipe is straightened to meet required specifications. The machining process begins with graphics-based cycle programming, where all tool paths and cutting parameters are defined for a complete multi-operation sequence. The workpiece is clamped once on a multi-axis CNC turning milling center capable of 4-axis machining, 3 linear tool movements, and 1 rotational axis controlled by the spindle holding the part. The operation starts with a roughing cycle using a turning tool to perform longitudinal turning along the Z-axis, removing bulk material, and preparing the cylindrical profile. This is followed by a program simulation to validate tool paths. After roughing, the finishing cycle refines the surface and brings the dimensions to tolerance. A tool change is automatically triggered, switching to a horizontal milling cutter for precise square milling on the rotating part. Then, a vertical milling tool is used to machine a central slot with accurate depth and width. Next, the machine performs milling from the center to enlarge a pre-drilled hole. A threading tool is then used to cut an internal thread from the center, ensuring alignment and thread integrity. Finally, a square-shaped pocket is milled into the surface. All operations turning, horizontal and vertical milling, hole machining, and threading are completed in a single setup with high precision. Leveraging full 4-axis synchronization, the production of LFD deep groove ball bearings follows precise German standards. It begins with heat treatment of high-grade bearing steel to achieve optimal hardness and wear resistance. This is followed by precision grinding, where raceways and surfaces are machined to tight tolerances. Super finishing then refines these surfaces to achieve exceptional smoothness, reducing friction and noise. Next, components undergo an intensive washing process to remove all contaminants. After cleaning, the bearings are assembled in automated lines under strict quality control. The inner and outer rings, steel balls, and cage are fitted with high precision. Predefined clearances and noise levels are ensured through electronic inspection systems. High-performance lubricants are applied, tailored to each application. Depending on customer needs, various sealing options are incorporated. Each step is closely monitored by integrated quality management systems. The result is a durable, low-noise and high-speed bearing suitable for demanding industrial applications, manufactured at a scale of over 100 million units annually. The 18-liter semi-automatic square can line begins with feeding flat metal sheets into a cutting unit, where they are trimmed to the required dimensions. The cut sheets are then passed through rollers that flatten and slightly curve the metal to prepare it for forming. In the next stage, the curved sheets are welded along the seam, creating a cylindrical or prismatic can body. These welded can bodies are then transferred to a forming station, where the machine squares the cylindrical body into a rectangular or square shape, conforming to the 18-liter can design. The top and bottom ends are prepared separately through a stamping process to create precise, tight-fitting lids. Finally, the can body is fitted with the top and bottom lids, which are mechanically crimped or seamed into place, forming a fully sealed square can. This semi-automatic process ensures consistent shape, structural integrity, and production efficiency, making it suitable for packaging products like paint, oil, or chemicals. After shaping, the steel bars undergo thermomechanical treatment, where the outer surface is rapidly cooled while the core remains hot, creating a layered structure. This results in a product with high tensile strength and excellent ductility. AKS bars offer 22% elongation, compared to 14% in standard bars. Bars are then cooled in a 12-meter-long cooling bed, the longest in Bangladesh, and automatically bundled. Final products are rigorously tested in a modern quality laboratory for chemical composition and mechanical properties, ensuring compliance with national and international standards. Unlike conventional producers using induction furnaces, AKS employs an electric arc furnace, capable of producing high-grade purified steel. This investment ensures that AKS TMT bars meet global safety standards, making them ideal for earthquake-resistant construction and modern infrastructure. The AKS-TMT, thermomechanically treated, steel bar production process, represents a significant advancement in the civil construction industry in Bangladesh. As urbanization increases and high-rise structures become more common, the demand for strong, reliable steel has become crucial. While many steel rods in the market are derived from molten scrap and lack purification, AKS produces 100% purified TMT steel bars using state-of-the-art technology, ensuring both safety and durability. The process begins with the import of prime quality billets, conforming to Bangladeshi, Indian, British, and European standards. These billets are reheated in a furnace and then cleaned with high-pressure water jets in the descaling unit, removing oxidation without causing spot cooling, critical for maintaining consistent metallurgical properties. The billets then enter the rolling mill, divided into roughing, intermediate, and finishing sections. AKS employs a unique combination of horizontal and vertical stands, eliminating the need to twist billets during shaping, thus preserving internal structure and strength. The microtension control system ensures uniform tension throughout the rolling process. Laser cladding restores worn steel guide rings by applying a durable SP43 powder layer onto the HR40 base. Used in glass blow molding, this process extends part life by renewing the surface without replacing the entire component. The production of high-quality train wheels using an automated forging line involves a series of precisely coordinated mechanical and robotic operations. The process begins with the loading manipulator, which positions the steel blank into the blanking press. Accurate centering within the press dies ensures symmetrical shaping. The press, delivering 9,000 tons of force, performs the upsetting stroke, forming the basic wheel profile. The sliding table then transfers the formed blank to the next stage. A robotic transfer manipulator removes the wheel blank and moves it through the line. Throughout the process, 3 industrial robots manage automated cooling and lubrication of both dies and blanks, maintaining consistent conditions. The system utilizes DNC-controlled axes for precision handling. During the wheel rolling phase, the blank is formed without the use of a mandrel. Instead, it is precisely shaped using web rolls, lateral rolls, and pressure rollers, representing cutting-edge rolling technology. Real-time online tool setting corrections optimize material flow and product consistency. Next, an oscillating needle embossing system applies a unique identification mark directly onto the wheel's surface. This durable mark supports full traceability. The finished wheel is transferred to a 3D laser-based measuring machine, which inspects dimensional accuracy using the latest metrology techniques. A fully integrated automation and piece tracking system monitors each production stage, documents measurements, and archives quality data for traceability and compliance. The Rolltech Wheels software optimizes forming machine parameters in real time, ensuring consistent quality. The forging line is capable of producing up to 280,000 wheels per year, with outer diameters ranging from 700 millimeters to 1,350 millimeters. The result is a robust, high-precision railroad wheel tailored to meet demanding operational requirements across freight, high-speed, and heavy-haul applications. With enhanced consistency, reliability, and reduced manual intervention, this process sets a new benchmark for modern wheel manufacturing, combining automation with superior metallurgical control for long-term rail performance. A severe overhead crane accident occurred in an aluminum smelter's pot line. A malfunction or operator error caused the crane to drop molten aluminum or equipment, leading to a dangerous spill across the floor. Such incidents highlight the critical importance of safety protocols, equipment maintenance, and operator training in heavy industrial environments, where even small mistakes can result in catastrophic, high-temperature accidents with serious consequences.